Wow, I have to say I'm very excited because we have very stiff competition. We were just in the green room and we're like, oh my God, there's so many celebrities in there. So thank you for coming to our session. So as mentioned, I'm Bob Lord.
I'm Dan Wallach.
And we're here to make smashing the stack less fun and hopefully not as profitable.
And we're from the government. We're here to help.
That's a good one. That's a good one. Okay, so just a little bit of orientation. So I'm from CISA, and you probably know CISA if you don't. Ooh, okay. And so one of the things I want to talk about is the fact that we're here because CISA's role is to help reduce the cyber risk of the nation and thereby the world. And so that's why we are here. Dan, why are you here?
Well, DARPA, among other things, has brought you things like the internet.
I've heard of that.
So
it's a mixed bag, to be honest.
Yeah, well, thanks to us, you now can be distracted by kitten videos 24 hours a day, 7 days a week. We're sorry about that. And we also care deeply about cybersecurity for our nation's infrastructure, including the military. And we are together to talk to you about memory safety.
That's right. But let's back up a little bit and talk.
Yes, let's back up.
Let's back up a little bit. Should we talk about secure by design just for a minute?
Just for a minute.
Okay, so most of you may be familiar with CISA's Secure by Design initiative, but for those of you who are not, let's talk a little bit about some of the norms that we have accepted in the world of software. We, for example, have placed the burden of staying cyber safe on the people and the organizations that are really least able to understand things like the threat landscape, even the phrase threat landscape. They're least able to respond with the right people who they can't hire and the processes which they may not know about, and they can least afford the necessary technologies. So this is the state of software today. And unfortunately, after a breach, what do?
We go to the press and complain.
And we absolutely, and we blame the victim.
Absolutely.
And so what do we say? We say, oh, tisk tisk, you should have patched faster. You should have patched all of the things. And we say, you know what? Part of this breach was tied back to things like lack of MFA. And we say tisk tisk, but we don't say like, why didn't the product recognize that this was an important and obvious thing to enforce? And we say things like, oh, you should have applied the hardening guide because the hardening guide would have told you all the things that you should have done to make that dangerous piece of software less dangerous. But we don't really talk about a loosening guide, which would be far more customer friendly. And we say, aha, you should have had a SOC, ignoring the fact that over 99% of American enterprises are small and medium-sized entities that have fewer than 500 people. So this is the state of affairs.
Which means that your SOC is, well, I know a guy.
That's exactly right. So that is sort of the umbrella that brings us here together. And for the rest of the talk, though, we're going to talk about memory safety. Is that okay?
That sounds like a great idea.
Okay, let's do that. Do you have any questions? You want to do an imitation?
Do I want to do an imitation?
Yeah. What's the deal with memory safety?
Yeah, you know, I wish I could do a good Seinfeld impression. I'm sorry, but what's the deal with memory safety?
Okay, it's pretty good. We got to keep working on it.
All right.
So let's start off with some basics. So Dan is actually a professor of computer science, so I'm actually very honored to be up here on the stage with him. And let's do a little coding, shall we?
I love coding.
All right.
So in my day job, before I joined the government, I taught sophomores at Rice University how to write software. And I thought I would give you a simple program. This is the kind of thing in an introductory computer security course that we would teach people how to exploit. This is a C program that takes some arguments from the outside and it compares them to a secret password, very secret. And if the password matches, it sets a little success flag, then it might have different behavior because it saw the password. How could there be a security vulnerability in such a simple little program?
It looks so simple.
It's so elegant. So it turns out the way C actually works, when you run this program, and you notice how there's more than 8 characters in the argument, but yet the buffer where it's getting copied is only 8 characters long. Because whoever needs more than 8 characters, come on.
Not for a password, no.
You laugh, but if you get the copy of the original Kernahan and Ritchie C programming book, they have this kind of example all over the place. So this was common coding practice in the 70s and 80s. Well, here's what it looks like in memory. So before we do the string copy, everything is nicely zeroed, or should be. We won't get into what it's often like. But afterwards, even though we were only trying to write into the buffer, we accidentally also overwrote the success flag. So whether or not you successfully matched the password, you're still going to do the potentially dangerous thing. That's just, C has no guardrails, no safety mechanisms, no nothing. So when we talk about these kinds of problems, how common are they? How severe are they?
It can't be that bad, because everybody's talking about it, Dan.
Oh my God, it is really not good.
Okay, you have some evidence to back that up, buddy?
We have better than evidence. We have data. We have charts and graphs and stuff. So these charts and graphs and stuff come to us from some Microsoft executives, which we gratuitously cut and pasted out of their slides. And what you see, this is from 2019. We have another one coming up in a second. The dark blue on the bottom are memory safety related security bugs. The light blue on the top are the rest of them.
You're saying it's mostly memory safety bugs, like the ones you just showed?
So this says that over a 12-year period, and Microsoft during the same time period was investing billions of dollars with a capital B in improving the quality of their software and removing security bugs. It was a major cultural shift in their company. They took it very seriously, and yet they continued to have problems for a whole decade. The same class of problems kept happening over and over. And this is a slightly more recent version of the same data. And dark blue became light blue became orange. But you'll see once again, this somewhere between 60 and 70. So maybe it's been slightly improving in more recent years. But we keep seeing the same problem year after year after year.
Despite actively working to solve this problem.
With some of the finest developers that they can hire, and Microsoft can afford the best.
Yeah, that's true.
But how about Google? They hire really good developers too, right? Well, here's some data from a blog post they put out in 2020. And this is which kinds of bugs are affecting Chromium. That's the engine inside Chrome. And what you'll see is, use after free, other memory unsafety, and are both examples of memory safety bugs. And again, around 70% of our high severity security bugs are coming from these memory safety problems, which are endemic to C and C++ and completely absent in other programming languages. Preview of coming attractions. So we're seeing this all over the industry.
Okay, so Dan, you've convinced me that there are memory safety vulnerabilities and that they might be statistically interesting such that we should try to solve them. But many of these kinds of vulnerabilities, they sometimes are just theoretical and it's really not possible to exploit them. So can we talk about what's really happening here?
It's not pretty.
Okay, so if you take a look at a number of different sources, one is Google's Project Zero. Not going to ask you to read this, so we will highlight the interesting part. They said that out of the 58 vulnerabilities that they found exploited in the wild, they were pretty meh or standard. That's not a good thing, because what they're saying is that about 67% were memory corruption vulnerabilities. There's that 2/3 number again. This is the sort of thing that we just see over and over again. It's almost like no matter which way you look at it, you get 2/3. There's some other ways to look at it where you get different numbers, but this is a pretty standard number, around 2/3. And so I guess the question we would ask is, and we have other slides that we had to cut that talk about a whole bunch of other different bits of evidence, but like in what other industry would we tolerate such unsafe tools and practices and components without the customers really speaking up? So that's foreshadowing also. So I think we have to ask ourselves what we should be doing about this.
Gosh, Bob, what should we be doing about
Well,
this?
there are many things that we can do. Since we're here from the government and we're here to help, we, of course, have been writing some white papers. And so you'll find that CISA has written a thing called the Case for Memory Safety Roadmaps. There's a link at the end, so you don't have to take a picture of this. Or you can take one if you want. So that's a diagram and an article that we wrote. There's also a CSAC, which is the Cybersecurity Advisory Committee to CISA. This is a group of distinguished folks from around the industry led by Jeff Moss of Black Hat and DEF CON fame. And they also put together a paper describing some of the things that organizations who are producing software need to think about with regard to memory safety. NSA, of course, wrote a paper on memory safety, and most recently the White House did a technical paper which is called Back to Building Blocks, which includes a number of things, including a big section on memory safety. So I think what we're seeing is that there's this growing awareness that this is a problem that is going to take an all-of-industry approach, and so that's why we are up here.
And believe it or not, it's not every day that you have all of these organizations. Also, we left off with the most important one. Consumer Reports also put out a similar advisory saying that memory safety is an important problem. How often do the NSA and Consumer Reports agree on anything? So we live in interesting times.
These are very interesting times. So, I think one of the things people say is, like, can't we just try harder? Can't we just try harder to get rid of these problems? And I think it's really important for us to acknowledge that we've tried everything.
Boy, have we.
And so there are all sorts of different techniques and technologies and processes that people have come up with, including some of these. Dan, what's your favorite of these?
Oh, I love fuzzing. Fuzzing is where you generate random inputs in a controlled way to try to make a program explode. Google has a huge OSS fuzz project where they use this to find bugs in open source software. And yet, despite that and all these other compiler techniques like control flow integrity and ASLR, nonetheless, we keep finding these bugs over and over and over again.
So the good news is, though, the cost of attack has gone up. Is that not true?
Yep.
Okay.
It's true. It's getting harder for the attackers, but the defenders have to cover all their bases. The attackers just have to find one weakness.
So a lot of people have spent enormous amounts of time and effort. Companies have been stood up. People have really thrown their backs into this, and it has helped to some degree, but it hasn't actually solved the problem. So I think that's one of the things that we have to think a lot about. But one of the things that we do know works is?
Throwing money at the problem.
Well, no, I was going to, no, the other one.
What can I do that's not involving throwing money at the problem?
Well, we could try to think about memory-safe programming languages.
We could try to throw money at developers to throw developers at the problem.
We could try that. So tell us a little bit about memory safety languages, memory-safe languages.
Right. So every computer language that's not called C and C++ tends to enforce memory safety as a function of how the programming language itself works. I taught all of our sophomores at Rice how to program in Java. Java doesn't have these memory safety problems. So then you say, well, let's just use Java everywhere. And I'm sure Oracle would love me to say that. The problem is that most of these memory-safe programming languages they're significantly slower, sometimes factors of 2, sometimes factors of 10. They also tend to use more memory. They do something called garbage collection to manage their memory. It needs more memory to run efficiently. And these things are problems, especially when you get to smaller embedded systems, lower power systems, systems where you're constrained. But if we could somehow get in there and have a memory-safe programming language that fit the C and C++ shaped hole, wouldn't that be amazing?
I think that would be amazing. And we know that memory-safe programming languages are interesting because they are more reliable. And for those of you who manage engineers, having fewer emergencies at the last second, that seems like a good thing, and I'm sure the engineers would agree with that. But also, there are a lot of other parts of an organization when you ship code that have to get involved too. So you've got the QA teams, and sometimes you have to have the comms people. You have to have the lawyers involved if you have to send notes to customers. And so having all of that is good, but also fewer breaches for customers is a good thing.
Right. There's sort of we're not going to go into the details of this, but it's sort of a well-known fact that the earlier you find a bug, the cheaper it is to fix. So if the bug has to go all the way out to the consumer before you find the bug, then finding out about it, getting it all the way back, QAing it, it's expensive. Whereas if we can, while the developer is still working on the software, say, nope, over there, fix it. That's the cheapest possible way to fix bugs. And memory-safe programming languages do precisely this.
So Dan, I've been told that there's a problem associated with memory-safe programming languages. That's all fine and good, but really replacing C and C++ is just a funny thing.
Right, so the problem is we have billions with a capital B lines of code. We can't just wave a magic wand and turn all that legacy C and C++ into something else.
And now we have a new programming language
called Rust.
Okay, so Rust is new, right?
Well, actually.
Actually, he's going to do the well actually thing.
Well, actually. So Rust got started in the mid-2000s. It was an internal project at Mozilla that was meant to help them write better, more robust web browsers. And it has taken off and has now gotten very much a life of its own. Without getting lost in the technical details of what makes Rust really go, the most important thing to understand is that Rust fits in every C-shaped hole that you have in your code. You can write Rust that interoperates with your C very nicely. Rust doesn't require a garbage collector, and the programs can be very small and memory efficient. Yet, they still have this compiler-checked memory safety guarantee.
And this is an interesting thing because we really have tried everything else. And so we've tried to make sure that we don't interrupt the developers and have to change their flow in order to have memory safe code. And it hasn't turned out the way that people have hoped. And so we've tried everything else. It's time to try something new is the general idea.
Right. And so even though people have been saying memory safe programming languages, they all had trade-offs. And Rust is probably the first one that doesn't have many of these trade-offs, and it's taking off as a result. I mean, I don't own stock in the Rust Corporation. There is no Rust Corporation. It's actually run by a not-for-profit, and it's all really volunteer-led effort, so a lot of corporate support. And because of that, it's become very, very popular. So, if you've never written a line of Rust code before, don't panic. But like we said, the compiler will guarantee memory safety. It has competitive performance. When you absolutely have to do something evil, you can. You can say, I am hereby doing unsafe things, and the compiler says, good luck with that, buddy. But it means that when you have to interoperate with the outside world, you can. Efficient interop. And if you are in various vertical markets, for example, automotive, their Rust is becoming qualified for use in these various vertical markets. So it's a whole other long discussion of what does it take for a programming language toolchain to be usable in automotive, in aviation, in defense. And the short answer is it takes maturity and documentation and a vendor to stand behind it. Rust is mature enough that all of those things are happening for it now. And because of the growing popularity, that means you can actually go hire somebody. I have spoken to defense contractors who say that they simply cannot hire ADA programmers. Anybody here ever program ADA?
Whoa,
Couple.
we got some hands. Okay, good.
Well, guaranteed job security for you. Right, but so because Rust, on the other hand, is becoming popular, it's cool, all the kids are doing it. And because of that means that we have a real shot at both hiring talent and retraining talent.
But I think retraining talent is very interesting. So I've talked to a number of different companies, and one of the things they say is they don't actually try to hire the Rust developers. What they try to do is hire very good C++ and Java programmers, and they have a boot camp process whereby they teach them how to program in Rust. And they have reported that, and this is of course just anecdotal, but what they've reported is that it only takes a few months for them to get fully up to speed and to become truly proficient. And then at the end of that, they don't have any, not only do they not have memory safety problems, they don't have race conditions, which is another topic outside of this particular talk.
And even if this memory safety stuff is just mumbo jumbo, Google recently put out a paper that showed that their Rust programmers were twice as productive even as their Go programmers. Go is also a memory-safe programming language from Google. So not only do you get memory safety, but developers seem to like it and seem to be measurably more productive once they get over the hump.
Your mileage may vary.
Yeah, offer not valid in all 50 states. Anyways, so.
Okay, so everybody says, this is the first of some of the objections, and people say, guys, you can't just go rewrite all of the C and C++ in Rust in a reasonable amount of time, maybe ever. I mean, we still have, COBOL and a bunch of other programming languages that are in production, so you're not going to be able to do that. And so there was a detailed study that we read, and it says basically the conclusion is that it's going to cost bajillions of dollars to rewrite gajillions of lines of code. Okay, maybe that was just us over beers. But the point is, I think it's very clear that this is not the plan that's going to work. You're not just going to be able to say, everybody stop what you're doing, rewrite. Professor Dan, I have a question.
Yes.
Everybody's talking about AI at this conference. Can't we just use AI?
It's true. I saw it on the building outside. It said AI.
It said AI everywhere. All right, so tell us a little bit about
Even
that.
people from the government have to talk about AI. It's required in our contract. So large language models are awesome, and you can ask them to do anything. But the problem is they're not always perfect. So I took Google's Gemini, one of the state-of-the-art language models, and I found a 180-line C program on the internet that was implementing a linked list, the same kind of data structure we ask college freshmen and sophomores to build. And I said, hey Google, please translate this to Rust.
Worked right.
And the particular data structure was violating one of Rust's pointer rules.
Looks fine to me.
And the problem is the head and the tail were both supposed to be pointing to the same thing, and that violates Rust's rules. And it generated code that this actually wouldn't compile. This wouldn't work. It should have used Rust's reference counters. It should have done a couple other things differently. Also, that stuff at the bottom where it's calling .clone, that means make a copy of it. So instead of actually building the data structure link by link, it was throwing out the old stuff and replacing it with the new stuff. So even though on the surface you look at this code and say, all right, it's like it's building my structure, it's got my impl for my structure, it knew how to do generics correctly, LLMs are super impressive. The problem is the output doesn't actually work. It's superficially reasonable, but it actually it won't even compile, much less run. So the key issue is hallucinations. Everybody heard about AI hallucination? You've heard about this perhaps in the legal context where some lawyers got in trouble submitting a brief to a judge that invented citations to case law that didn't exist. This is the computer version of it. It invented software that would never have compiled, and it doesn't know any better. It's like, hey, I got your solution here for you. So the key thing to understand is that LLMs are a very useful tool, but they don't think the way a programmer thinks. They don't understand, wait, I'm building a data structure, what are my invariants? All the things we train college freshmen and sophomores to think about, LLMs can't do. So the key observation I want you to come away with is not the particulars of how Rust works. You're welcome to learn that on your own time. It's an awesome, fun programming language. The key observation is that LLMs are limited. They're useful, they're helpful. They might improve your productivity, but you can't rely on them without knowing what you're doing.
Okay, okay. You've convinced me, maybe in the future, not today. I've got another idea.
All right, hit me.
Let's do it in hardware.
Yes! Wait, we already have hardware.
No, I mean new hardware that makes things memory safe without you having to do a lot.
So we're going to make new computers that solve all the problems with the old computers.
Let's do it.
Have we heard this before? Sure. Well, we can try. So there are, some of you might have heard of Cherry, which is a research project from SRI and University of Cambridge in England.
How many people have heard of the Cherry project? A few?
A couple of you.
Okay, that's good.
So the Cherry people have a very old idea that if you know how computers worked in the 1960s, back in the old days they were very experimental and no two computers worked in slightly the same way. It's really cool. So they're resurrecting some very old ideas from computer science and saying, what if old idea but new design? And so the idea of Cherry, and by the way, they're working with ARM. This is a prototype Morello chip that ARM fabbed in small volume. And the idea is that we're going to build these kinds of memory protection into the CPU itself. So then your C program running on Cherry hardware would, the instruction set architecture, the way the machine works, it would be able to watch what happens and be able to say no without forcing you to rewrite your program. So you get your existing C and C++ program, you have to port it to Cherry. But the effort of making your code work on Cherry is not all that different from the effort of, well, you had it working on x86 and now I give you an ARM. Okay, you have to port your code. It's not that bad. They've already been working. They've got operating systems, hypervisors, compilers. They've got a browser running on it now. There are Cherry RISC-V implementations floating around as well. RISC-V is the hot new thing because you don't have to pay a license fee to anybody. So for the people who are counting pennies on chips, that really matters. So Cherry RISC-V is so Microsoft did a design that Google is thinking about possibly deploying, but when I spoke to a Google guy this morning, he was like, no comment. I'm like, yeah, but what about no comment? But didn't I hear that? No comment. So you didn't hear it from me that Google is doing something really cool. But anyway, so this will be coming soon to certain devices near you, but probably not your phone or your laptop for a while. But back to our example. If we had a hypothetical Cherry computer running the same program, then here's what would happen. When you were doing that string copy, it would say, wait a minute, you went over the edge. The buffer is exactly this big, and when you tried to write past the end of the buffer, the hardware will halt the program and say, nope, not allowed. So your program will terminate in a safe way rather than becoming exploitable in hardware. Super cool, if only we could just replace all the world's computers.
Well, instead of replacing all the world's computers, another idea I had is maybe we'll just do it incrementally. How's
Okay, that seems like a great idea. So we're going to replace the computers incrementally, or?
Well, we could do all of those, and so we should probably have parallel tracks, but let's just talk about the software.
Okay, let's replace the software incrementally. So Google has been working on this for several years, as have many others, but Google gives us some good data, so we, of course, cut and paste. So this is the Android code base, and even though Android apps are mostly written in Java or Kotlin, which is another safe language, there's still a lot of C code and C++ code in the guts of Android. And what they've been working on is, for the last, since 2019, every year they've been finding the sketchiest parts of Android and tearing those bits out and rewriting them in Rust. And they've been turning this crank for several years now. And what they've found is if you turn the crank year after year after year, you actually improve quality. Crazy stuff. So it's working for them. What they've found, the clicker has died. Oops, that's the wrong button. There we go. I was pressing the laser button. Hopefully I didn't zap anybody. I'm terribly sorry. Yeah, I have a cool laser. Anyway, what they've found is they've dropped from 76 to 35% of total vulnerabilities by virtue of turning this crank year after year after year. 35, you might notice, is greater than 0, but is substantially less than 76.
And we should also note that this 2022 was what they reported is that is the first year in which memory safety vulnerabilities do not represent a majority of the Android vulnerabilities. So this is a huge change.
So maybe we could do that.
So we have an existence proof, and sometimes what people need is an existence proof. And have you noticed that we've been talking not just about the technology?
We're talking about the engineering process.
So I think this is an important observation, and a lot of times we get just caught up in the technology, and we need to talk a lot more about the processes and the incentives behind all of these things. So incentives is going to be a key thing that we need to monitor over time. And so what sort of things do we want? Well, I think we want to start making more demands on the software providers themselves. And so when we talk about the demand signal in terms of the incentives, we want the software providers to start working on this with a real sense of urgency. So we know that they've been trying over the past 20, 30 years to reduce the prevalence and impact of these memory safety vulnerabilities, but we really need to have a renewed interest in moving to memory safe programming languages. And you know, honestly, a lot of these things kind of look like the stages of grief, and I don't mean that to be like disparaging of anybody, but you sometimes have to go through those stages of denial and anger, and you got to get into bargaining. And once we get into bargaining, now we can start to see some progress. And things like code analysis and sandboxing and all those other things, if you just keep doubling down on the old techniques, it's just delaying the inevitable move to a memory-safe programming language. So we know that this works, we know that this can drive down costs, and we know that it drives down risk. There are some speed bumps. We're going to talk about that in a second. And it's often the case that people focus on the speed bumps, they focus on the potholes, and they don't focus on the end state. And so one of the things, if you're software developers, think a little bit more about focusing on what you can do, not what you can't do. And every software manufacturer is just different. They have different constraints, different legacy code. Every one is different. But if you can focus on the first steps in that journey, you're going to start making progress, probably faster than you think. And to do that, we want the software companies to start making plans to make that migration starting this year. And we'll talk more about the plans in a second. But we really want a memory-safe roadmap. So rather than just think about it or have some internal meetings, we want to have the software companies publish their memory-safe roadmaps that explain to the customers and the public what it is that they're going to be doing to solve this chronic class of vulnerability. So, what goes in to a memory-safe roadmap?
Hopes and dreams.
I thought you were going to say throwing money at it.
Oh yeah, that too.
Okay.
Money. Hopes, dreams, and money.
Hopes and prayers. And so one of the things that we want to think about is the defined phases. So how are you going to chunk the work? What piece of the journey are you going to pick off first and start to drill down on? What are the milestones that you're going to be using? How about publishing? Now, this is a bold one. The date after which the company will write new code or start new projects with a memory-safe language. So that may be a few years out. Companies don't start all new product lines on a whim. And yet, if you were to say after this date, any new product that we produce will be built in a memory-safe programming language, that would help. Developer training plan. We talked a little bit about hiring the people who are doing the work, not just hiring the Rust programmers, but hiring people who can code and teaching them what they need to do. The internal training plan is going to be very important. Dependencies. There are just a ton of dependencies that, that organizations are dealing with. It's going to be a problem. A lot of your code is going to be built on open source libraries. Some of those, maybe many of those, maybe most of those, are written in C and C++. So a plan to deal with that particular problem is going to be key. And again, everyone is going to be different. And then regular updates. So, not just publishing once and forgetting it, but publishing maybe quarterly, maybe annual updates to the roadmap would be key. And we think about classes of vulnerability more and more. It's not just enough to think about playing whack-a-mole with a particular vulnerability, but to start thinking about entire classes of vulnerability. And to that end, there's a field within the CVE data structure, which is called CWE, which is the weakness enumeration. And that's the thing where we talk about the root cause. And one of the things the entire industry can do is just get better about filling out those CWE fields, because that tells us all what kind of defect this is. Not just that this particular thing is broken, but what patterns do we see? And for bonus credit, stating your commitment to helping others get through this journey. I think that's going to be key. And we talk about, in the Secure by Design world, we talk about leading from the top as one of the core values, the core principles. And so having the CEO sign it rather than a member of the technology group, that's going to be a strong signal to the customers that you are really thinking about moving forward. Okay, there's some counter arguments.
No, there aren't.
Okay, good, we're done. Thank you, drive safely. All right, so people say, oh, memory safety is not a silver bullet. Well, nobody said it was. Attackers will just get in some other way. Yeah, but we want to change the economics. It's not just a matter of changing that particular programming language. We want to raise the cost of attack. There's still going to be logic bugs, Dan. That's one of the things I've heard. And I think that's all true.
All true.
That's kind of what we want. We want them to not be able to use memory safety as the hook that gets them access to the entire system. We want them to do something else. C can be made safe, is that true?
Yeah, it's called rewrite it in something that's not C.
Right. We've heard that C++ will catch up. Certainly possible. There are people working on something along those lines. It's entirely possible. Rust is too hard. There's a little link there to what is that, an online book?
Yeah, so just a brief plug. There's a great group at Brown University that's taken the Rust book and the hardest chapters of the Rust book. They've rewritten them and added exercises and questions and things to help you learn the bits of Rust that are considered the trickiest bits. So there is active work ongoing to make Rust easier to learn.
And so I talked a little bit about the stages of grief, and I think we hear a lot of these complaints from people, and some of these have a germ of truth in them, but the main thing to take away is that memory safety is the foundation of all security. If you can't control what the CPU is doing, if you don't have control of the memory, you really have no control of your system at all.
Right. Another way of looking at it is memory safety is a property that means you can look at your software and read the program, and you don't have to read it with a devious mind. What if I could overwrite this buffer and squish that buffer? What if there was this, when your program is memory safe, it does what it says and it says what it does. And that helps you analyze it, that helps you improve it, and that means you don't get these surprising behaviors.
That's right. And so let's talk about some of the other speed bumps that people mention on a regular basis. Legacy unsafe code. You're going to have lots of unsafe code. Do we have any magic bullets for that? Silver bullets?
Turn the crank. That's our magic silver bullet.
So I think these are legitimate things that we need to study, and I think it's worth, if any of you are academics, these are areas of real interest. IoT and ICS, so if you're running like OT systems, if you're doing operational technology, if you're doing ICS, industrial control systems, it turns out that the development environments and the debugging environments in those systems is not identical to the ones that you would get on your desktop or in the cloud. And so it is a valid concern that we don't have all of the same tools and technologies and processes in all environments that we do in some environments. So I think there's areas for maturation there. We see some progress. You mentioned the, what was the other system, the automotive system?
Oh yeah, so that was, yes. So
I don't remember.
I forget the number. It was something ISO 26262.
Some ISO thing.
There's work in progress to help bring Rust and other safe programming languages into these vertical markets.
Right. So we see some progress there, but there's still lots of work to do. Funding. People have rightfully noted that there are different foundations that help with memory safe programming languages. They don't always get all of the funding that you would think, given that our entire economy and infrastructure is all built on them. So a valid observation there. And customer demand. I think if we all simply demanded the memory-safe programming languages and we asked for a memory-safe roadmap from companies and we started to make purchasing decisions based on those, the problem would just kind of shake itself out, would be my opinion. And so we definitely need to have more educated customers and we need to have real demand signals. And you know more about this than I do, but I'll tell you the one observation I have is that my nephew just graduated college and he was talking about a project he was working on, and I said, oh, what are you going to write that in? And he goes, oh, well, C++. And I said, don't you want to write it in a memory-safe programming language? And he said, what?
Yeah, so for better or for worse, I mean, okay, at the school where I am, C and C++ show up in like one class. Otherwise, students never really use it. But we are not, every school is different. There's still a lot of kids being trained to do this, and there's still a big demand signal. So,
from industry.
From industry, because
right.
The industry still wants to maintain their existing code. Can we migrate education to teach Rust? Well, I mean, education moves slowly, but it's already the case that most freshmen are taught in Python or Java, not C++. So memory-safe programming languages already have a foothold. So we're getting there.
So there are some legitimate areas for improvement, let's call it, that we all have to think about, and there are more in addition to these, but I think we need to acknowledge that this is not going to be a trivial exercise. Having said that, as we've seen in prior slides, there are companies making that move, and they're doing pretty well. So what can these great folks who came to this session rather than all the other sessions, what can they do to become a little bit more up to date? I would say there's a couple things you can do. One is you can read any of those two papers. So the first one is the CISA document, which is the Case for Memory Safe Roadmaps, where you can read more about exactly what memory safety is, and it'll also tell you a little bit about what a memory safety roadmap might look like. And the other is the White House paper that I mentioned. I mean, the White House doing a memory safety paper, that's kind of interesting.
It's not every day that I end up on Zoom conferences with people who work in the White House who are picking my brain about memory safety.
So I think that is...
We live in interesting times.
And both of these documents are, I would say, pretty readable. So please check those out. Then the other thing I would suggest is that you start to watch for these classes of vulnerability. Just like in general, look for classes of vulnerability and see if you can get good at spotting which vulnerabilities, when you see a CVE, see if you can guess by the title if it's a memory safety vulnerability or not, and then dig in a little bit to kind of see. And over time, you'll get pretty good. I'm pretty good at this. Are you pretty good at this game?
I suck.
I love this game. I love this game. So I would encourage you to start tracking that. And again, this is part of CISA's larger effort to try to get people to think more about classes of vulnerability, not just individual defects. And over the next 6 months or so, one of the things that you can really do to help us is to start to ask for safer products. Just in general, under our Secure by Design program umbrella, that's going to be helpful to driving products to be more secure. But if you start by asking for the memory safe roadmap, that's an amazing, specific, crisp thing that you can start to ask them, and you can send them those other documents if they have no idea what you're talking about.
And you could imagine this happening at the consumer level. You're buying a new smartwatch, all right. Hey, smartwatch vendor, Garmin, Apple, Google, Samsung, where's your memory safety roadmap? Or at the corporate level, we're buying a new enterprise CRM something or other. Hey, enterprise CRM something or other vendor, where's your memory safety roadmap? As a customer, you have power.
And some of the links that I'd mentioned before are here. You can also check those out online or take a picture of this and jump in anytime you like. So I think that those are the prepared remarks that we have.
And we would love to take your questions.
We could do that.
Thank you.
Hi, thank you, gentlemen. I came for the free microwave, but I'm buying the memory safe roadmap. My question is about, as a developer, I am, of course, a unique and beautiful snowflake. My code is perfect. I develop in a secure language. But under the hood, 70, 80, 90% of all my code is really open source. And that open source, there's a lot of C, there's a lot of C++. I may have some visibility, but I can't turn the crank on my open source software dependencies. So how, is this a false sense of security? Yes, I'm using Rust or Python, but under the hood, it's all something else?
So you're absolutely right that modern software is not something you build from scratch. Modern software, you stitch together other components provided by other people. And when you're in the Rust ecosystem, you have crates from other Rust providers. When you're in the Python system, you deal with pip or PyPy or whatever, one of these, Conda, all these different environments. And especially Python, underneath there's a lot of C code because Python itself is way too slow. You use NumPy or Pandas. Underneath, everything is actually C code. So what do? Well, to some extent, if you are a consumer of a package like NumPy, why not also become a maintainer? Offer them patches, go fix something, help. These open source projects exist because people like you need a feature or need a bug fix. Why not also do a security enhancement? If you've got a spare moment and your company is willing to spare your time, go contribute back, go help.
And I think we talked about the demand signal for finished products like consumers and for enterprises. I think the same thing is true for open source, the whole ecosystem. So that's not going to solve the problem. It will help elevate the awareness of the problem. And I have tremendous faith in the open source community to start nudging itself in the right direction. But it needs to hear from you, the people who are building on top of that phenomenal infrastructure, that this is a priority for you. How that's going to shape out, I actually defer to people like you, but if you start to create the demand signal, I think the right thing will start to happen over time. Over time.
Keith McCloskey with ECS. I want to thank you guys. Very entertaining, very informative. I love your dynamic. I was just in the session on software liability with James and Bruce and Nick, and the connection to what you guys are talking about, and how do we make sure that organizations that are building the software and even having some degree of responsibility over the open source community, how does the recommendations around a memory-safe roadmap feed into that? Because there's so much correlation and opportunity to use the carrot and stick side of this so that we can, as consumers, take advantage of it.
Yeah, I wish I could have been in the other session. Yeah, okay. So I think the questions of regulation and liability are very good. I think one of the things that I would point out, though, is that when we take a look at things like the history of automotive safety, you'll see some of our blog posts, you'll see that we are big fans of things like Unsafe at Any Speed, which is a book that came out in 1965. It really revolutionized the safety of automobiles as we knew them then. They're completely different today as a result of that book. And one of the things, though, if you start to go back and look at things like the history of vehicular death per billion miles driven in the United States going back to like 1920, you'll see that there was tremendous progress made before 1965, and that a lot of what happened was that there had been a plateau, and then the book came out, the Department of Transportation was created as a result, and then it started to come down again. I think there's just tremendous opportunity for us as a community to start to really acknowledge that the software that we have today is largely not safe. Memory safety is just one example of that, and we need to start to self-regulate to start to say, what should we be doing? I think anyone in this room, if you open up any feed from any of your social media feeds, if you take a look at the news, it is absolutely a fire hose of breaches and ransomware and misery. And I think everybody who takes a look at that should just start to think about seeing themselves as the hero in that revolution. And yes, there are going to be other people who are going to be talking about all that stuff. I have other thoughts on it, but I want people to not focus just on the stick. I mean, I want to take a look at I want to be inspired by the things that happened in automotive safety and other industries before regulation. I say, let's just get ahead of this curve. So that would be my plea to people, especially the folks in this room.
Yeah, I'm not sure how much time is left, but in your question, you were talking about market forces and like the customer demand, but I was wondering about the ability of the influence you could have in academia, talking with universities and essentially directing programming into like the more memory safe language like Python, Java, JavaScript, that kind of thing, and trying to essentially get them on side in this kind of this move.
If you think academics can be herded, you haven't hung around with too many academics. So to some extent, academia will follow demand signals from industry. And if a particular university is falling behind, the students will self-teach themselves things that the university isn't teaching them. So to some extent, academia is not really the hard problem here. The hard problem is creating the industrial desire and demand and scale. And I think if we can create an impetus that people care, and it's a question that they're asking when they're purchasing products, at whether it's consumer products or enterprise products, it's the same problem. There has to be a demand signal.
Right. But yeah, sometimes I feel that academia can have an influence. And basically, that could be a starting point as well. So it's kind of an idea. I thought my son's learning Python because he was learning about the advantages of it, and he's basically decided to just go with that.
All right. I want to make sure we have time for one more question.
Thank you. Maybe following on the question about academics and that relationship, I was very encouraged to see that the White House paper made a mention of formal methods. And I just wondered if you would say anything about the adoption of formal methods, related area of expressive static typing, and that sort of thing in remaining time. Thank you.
Okay, so formal methods is the next step after memory safety. Once your program means what it says and says what it means, now does it actually mean what it's supposed to mean? So once you have memory safety, that's the new floor. After that, you might try to prove properties about it. Like, I don't know, my cryptographic implementation is sufficiently randomized so that way somebody can't predict something. That's an application-specific property that you prove, typically assuming memory safety below. So formal methods are the next step. Memory safety is the foundation. They're telling me to stop. Thank you all so much.
Thank you all very much. Appreciate your time.